You have entered a fully immersive map of the universe. It's the most detailed model of the universe to date based on measurement of visible and invisible light, obtained from telescopes located both here on Earth and in outer space. We've charted out a visit through this data for you. Now sit back as we take you on a ride through this virtual universe, starting from the great blue planet we call home. This is the night sky from Geneva. The International Space Station is making its way across the sky against the backdrop of the Milky Way. Let's go into space and see the International Space Station. It's orbiting at an altitude of 400 kilometers above the surface of the Earth. Astronauts need a few hours to travel from the Earth to the International Space Station. At the speed of light, about 300,000 kilometers per second, the maximum possible velocity, the journey takes only 1,000th of a second. Let's see what else is orbiting our planet. Each dot represents an artificial satellite. Sputnik was the very first satellite launched into orbit in 1957. Since then, thousands of artificial satellites have been sent around the Earth. About 3,000 are currently active. The majority of them populate a variety of orbits, extending up to an altitude of 36,000 kilometers. It takes light only 1/10 of a second to go from a satellite down to Earth. Our oldest satellite is, of course, a natural one, the Moon. In 1969, we set foot on the Moon, and it remains to be the farthest place that has ever been visited by a human being. At 380,000 kilometers from the Earth, it's like traveling around the globe almost 10 times. While 4 days were necessary for the astronauts to reach the Moon, it takes light only 1 second to travel this distance. Earth is 151 million kilometers away from the Sun. Light from the Sun is 8 minutes and 20 seconds old by the time it reaches Earth. Now let's go towards Mars, the fourth and last of the rocky planets. Here we see Phobos, one of Mars' satellites. Mars has another satellite called Deimos, and they both measure about 20 kilometers across. Mars is 250 million kilometers away from the Sun. Light from the Sun is 14 minutes old by the time it reaches Mars. Mars is by far the most explored planet other than Earth. Beyond the 4 rocky planets, one encounters the 4 gas giants of our solar system: Jupiter, Saturn, Uranus, and Neptune. Launched in 1977, Voyager 2 is the only space probe to have visited all 4. Now we're going to hitch a ride with Voyager 2 back when it passed by the giants. In July 1979, Voyager 2 made its closest approach to Jupiter. In August 1981, Voyager 2 made its closest approach to Saturn and took detailed pictures of Saturn's rings. At 1.5 billion kilometers away from the Sun, that's twice the distance of Jupiter, or 10 times that of the Earth. Light from the Sun is 1 hour and 23 minutes old by the time it reaches Saturn. In January 1986, Voyager 2 encountered Uranus. At 3 billion kilometers away from the Sun, sunlight takes 2 hours and 46 minutes to reach Uranus. In August 1989, Voyager 2 encountered the 8th and farthest known planet of the solar system, Neptune. At a distance of 4.5 billion kilometers from the Sun, that's 30 times further away than Earth. Sunlight is about 4 hours and 8 minutes old by the time it reaches Neptune. Let's fast forward to now. Voyager 2 is still out there, as is Voyager 1, also launched in 1977. 3 other space missions are at the outskirts of the solar system. Pioneer 10, launched in 1972, Pioneer 11, launched in 1973, and New Horizons in 2006. The solar system extends beyond the well-known planets into a reservoir of small frozen bodies named the Kuiper Belt. This reservoir is also host to larger bodies. Pluto and Eris are 2 dwarf planets that you can see here by their orbits. The farthest known dwarf planet is called Far, Far Out. Discovered in 2019, it's 140 times further away from the Sun than the Earth. Light from the Sun is 20 hours old by the time it reaches Far, Far Out. From anywhere within the solar system, the patterns in the sky made by the stars and the Milky Way galaxy are still the familiar ones that we see from Earth, outlined here in blue. But when we leave our solar system, our perspective changes and the patterns of the stars begin to shift as we approach the closest neighboring star, Proxima Centauri. The light we see from Proxima Centauri here on Earth is already 4 years old. In other words, if we could travel at light speed, it would take us 4 years to reach Proxima Centauri. We say then that Proxima Centauri is 4 light years away. Compare this to the actual speed of Voyager 1, which is about 75,000 kilometers per hour. It would still take Voyager 1 no less than 60,000 years to reach Proxima Centauri. The patterns of the constellations continue to change shape as we move even further out to a distance of 50 light years. We now reach the star called 51 Pegasi, or 51 Peg, which is host to a planet called 51 Peg b. Planet 51 Peg b is called an exoplanet, since it's located outside of our own solar system. Discovered in 1995, it's the very first exoplanet ever discovered, opening up an entirely new field of research in astronomy. When the 1936 Olympic Games were broadcast, the radio signal was strong enough to reach outer space. Since then, these broadcast signals from Earth have only multiplied. So for the past 80 to 90 years, we've essentially been sending signals into space. These signals have been traveling at light speed ever since, meaning that they've reached a distance of up to 80 to 90 light years away. That's the size of the sphere shown here. No human has ever been this far from Earth, but it does mark the reach of human-made signals into space. Say goodbye to the stars of the constellations now, as we zoom out to see all of our neighboring stars, the stars that make up our very own galaxy, the Milky Way. The Milky Way is a spiral galaxy, and our Sun is just one of its 200 billion stars. The Milky Way measures about 100,000 light years across. Since the discovery of the first exoplanet 51 Peg b, nearly 5,000 other exoplanets have been discovered. Each dot seen here corresponds to an observed exoplanet. So far, most of these exoplanets have been observed in the neighborhood of the Sun. Astronomers continue to build more powerful tools to scan deeper regions of our galaxy in search of more exoplanets. Based on observation, it's likely that almost every star in the galaxy has several exoplanets. The Milky Way is composed of its 200 billion stars, but also of gas and dust. Recently formed bright stars less than 5 million years ago heat their surrounding gas, forming red patches distributed all along the galactic morphology. The Milky Way is characterized by its flattened shape and the presence of large spiral structures. The stars of the Milky Way look motionless to us, but thanks to the combination of observation and complex numerical simulations, scientists now know that spiral galaxies are evolving and formed billions of years ago. If we speed up time, we can simulate the motion of the Milky Way. Notice how the spiral arms are continuously formed and destroyed. This is due to the combined action of gravity and rotation. Stars are constantly being born in the red regions that show very hot gas. In the 1970s, careful analysis of the way spiral galaxies rotate revealed one of the most important conundrums of modern science. Stars and gas at the edge of galaxies rotate faster than expected. Either a mysterious, unseen form of matter is driving this faster rotation. This hypothetical matter is called dark matter. Or our understanding of the law of gravity is incomplete. Let's move away now from our galaxy. Our Milky Way is not alone in the universe. It's actually surrounded by tens of smaller satellite galaxies seen here as hazy blobs of light that are either elliptical or irregularly shaped. The majority of the satellite galaxies are very faint, up to 1 million times fainter than the Milky Way itself. But some of them are almost as bright, like the Large and Small Magellanic Clouds that can be seen from Earth's southern hemisphere with the naked eye. At 2.5 million light-years away, we reach the Andromeda Galaxy, also known as M31, the nearest spiral galaxy to our own Milky Way. Slightly further away, we encounter the Triangulum Galaxy M33. Together with the Milky Way, these three galaxies and their families of dwarfs form what's called the Local Group, a group of more than 140 galaxies spread over a structure that extends across 20 million light-years. What is the destiny of our galaxy? The two largest galaxies of the Local Group, the Milky Way and the Andromeda Galaxy, are expected to eventually collide in about 6 billion years owing to their mutual attraction. The collision will give rise to a single, giant elliptical galaxy as seen in this numerical simulation. The impact of such a collision will of course have limited influence on the future of humanity, as the Sun will have already ceased to exist for more than 1 billion years. Mergers of galaxies and larger structures are ubiquitous in our universe. Let's zoom out to cosmological scales at a distance of hundreds of millions of light-years. That's the equivalent of thousands of Milky Ways across. At these scales, we discover the large-scale structures of the universe. Numerical simulations like this one show the merging of matter into complex structures over billions of years. It shows us that galaxies are not distributed evenly in space, but rather form giant filamentary structures called the cosmic web. At the intersection of those filaments, galaxies assemble together to form gigantic clusters of galaxies, seen here as bright round blobs. As time goes by, the clusters acquire greater mass from within the cosmic web filaments, while the voids and the filaments become more and more pronounced. Clusters of galaxies may contain up to hundreds of galaxies, covering a volume of about 1 million light-years in size. They contain a large quantity of gas, reaching temperatures as high as tens of millions of degrees. Scientists study the evolution of clusters and the cosmic web in order to determine the energy and matter components in our universe, as well as the law of gravity on large scales. While the cosmic web is traced by the light emitted by galaxies, the numerical simulations tell us that these large-scale structures are dominated up to 80% by dark matter. The filamentary structure that emerges in numerical simulations is in perfect agreement with observation. Beyond the simulation box, you can see the most comprehensive database of galaxies as measured by the Sloan Digital Sky Survey, collected throughout 20 years of observation. It consists of the largest, most complete 3D map of observed galaxies in the universe to date and reveals the true large-scale structures of the universe. The data contains artifacts since it's collected from telescopes on Earth. Light from distant galaxies is essentially obstructed by the Milky Way, never reaching the telescopes on Earth, and therefore leading to gaps in the data, seen here as black voids. Each bright object corresponds to a galaxy. Each galaxy contains hundreds of billions of stars, and very likely hundreds of billions of exoplanets that could potentially host life. The universe as we know it appeared 14 billion years ago in an energetic explosion called the Big Bang. As the universe expanded, it also started to cool down. The first particles started to form until electrons and protons combined to produce hydrogen, the most abundant element in the universe. When this happened only 400,000 years after the Big Bang, light could travel freely in space for the first time. As the universe continued to expand over billions of years, this first light stretched into longer wavelengths and is detected today as microwaves. This relic light of the universe in its infancy continues to reach us even now, and it's everywhere. It's called the CMB, the Cosmic Microwave Background Radiation, and the colorful pattern seen here is the measurement of this relic light as seen from Earth. The CMB sphere corresponds to the size of the observable universe and measures about 100 billion light-years across. The CMB is the very first picture of the early universe and shows fluctuations in the distribution of matter. Let's look again at a simulated portion of the universe. At these early times, the universe was nearly homogeneous, only imprinted by tiny temperature and density fluctuations. Over time, under the influence of gravity, these initial fluctuations are amplified and generate the cosmic filaments. At the intersection of those filaments, the accumulation of matter is sufficient to form the first stars. The assembly of those stars become galaxies, and the dense regions of galaxies form clusters of galaxies. Simulations like this one allow us to understand the emergence of these large-scale structures. Let's zoom back through the data, through the different scales, back home. This modern view of a dynamic universe started 100 years ago with a theory of general relativity, a theory of gravitation, by Albert Einstein, boldly standing on the shoulders of giants like Copernicus, Kepler, Galileo, Newton, and many others. As scientists collect more and more data, as theories evolve, our understanding of the universe will also evolve. We're home, Earth. It's from Earth that we're exploring the depths of our universe. It's from Earth that we're looking at celestial light coming from the past that tells us of the history of the universe, an archaeology of light. Put into perspective of this cosmic journey, our planet is tiny and its existence is ephemeral. It has water. It has life. We wouldn't be here without this blue planet. What a precious opportunity it is to be alive on Earth.